Yep. So, I hope you guys can see me. Okay. So I'm starting off with the first paper that I have decided, which is linguistic regularities in continuous space word representation. Okay. To attend or to go through this live streams, I would suggest you need to have a basic idea of deep learning. I suppose you can have a little bit idea about how feed-forward networks work, how uh, neural networks works, or how RNN works. So, a machine learning and deep learning's basic idea that's needed for you before you even try to read these papers. So, I won't be covering like the basics of deep learning as such, but if at all, if there's a need for an explanation at any place, I will try to give that as much as possible. Okay, so the first paper that we have is linguistic regularities in continuous space word representation. It's almost like a decade old, uh, but it was the first attempt, I suppose, one of the first attempts to represent words um, with some kind of a context or some kind of a meaning in some vector space. That we see now. We have embeddings for everything. We represent these words as embeddings. But before this idea came into being, we had very discrete measures. What we would do is we would have these models that would just predict the next word given the previous words. Well, there was no relationship. It could understand the context of anything. You can call it this paper as one of the uh, first ideas into it. So the most important as idea in this paper is vector offsets. What it really means is if I have this very popular example in deep learning or NLP as such is uh, let's say you have a vector for king, you have a vector for queen, and you have a vector for a man, and you have a vector for a woman. Okay, if I say vector of king minus the vector of man plus vector of queen, a vector of woman, it would give you the vector of queen or the you know after the arithmetic operation is operated upon, like the vector of king minus the vector of man plus the vector of women, it will give you another vector. And if you do a similarity search on this vector, you would find a vector that is close by to the word queen. That was the idea here, that if there's a relationship between two things, this relationship will have kind of similar vectors, you know. So that's what we are going to see in this paper as such. I hope you guys can hear me. Okay. Cool. So coming to the whole paper, let's start off. Just give me a second. Let me just check everything's okay. Okay. Ah, Continuing. So I'm a little bit, under the weather, so my voice is a little mumbly, I suppose, but uh, we can deal with this, right? Okay. So the continuous space language model demonstrated. Sunrises across various stars. In this paper, we examine the vector space word representation that are implicitly learned by input. Representation of surprisingly good at capturing syntactic and semantic. These are two ways of analyzing, evaluating any kind of models or language parameters. We don't have it like it's still a method, but uh, we we don't really use it now, I suppose. That is syntactic and semantic regularities in languages. What it means is we will see in the future as we go along this paper what syntactic and semantic regularities in languages mean. Okay, so I have given the example. You see, king minus man plus woman. It should give you a vector that is close to queen. So before you know understand what is happening, you need to have idea of vectors, how vectors, what vectors are, or what is a dot product, what is a cosine similarity as such. So I will give you a brief about this. Vectors is anything that is in a vectors are these you might have already known vectors have a direction and a magnitude, right? So if it were a vector in a 2D space, it will be in a xy coordinate and pointing towards one direction. Okay, so this would be one vector. Okay, so think of this as king and I will show you a picture as well here. What they do, yeah. So this is a vector for king. Okay, there might be a imagine there's a big Cartesian plane here. Okay, this is the Cartesian plane coming from here to here, here to here, and then this is the vector for king. This is a vector for kings. Vector for queen. This is the vector of queens. It all the vectors are from the origin of the Cartesian product. I hope that makes sense. Okay, if I can draw like this is the one and this is the other one. So this would be a vector in the direction of king, kings, queen, queens. So now what we are represented in is this basically um, these vectors in 2D is a 2D, right? It has two dimensional x and y in 2D. But when we actually do it, we will use n dimensions, a lot of dimensions actually. We can go hundreds, we can go thousands of dimensions as well. Depends upon what are the use cases. But yeah, we can have thousand of dimensions, so it will be in a hyper dimension and dimension space where all these vectors will live. Now our idea is basically in this paper basically what when we say uh, we will learn the representation of any words as such, it means is that uh, words that are similar to each other. For example, a word that is say a dog and a cat, so they are both are animals, so they would be nearby in the vector space. A word for a word like a dog and a chair would be completely different, so they would be in a very different places. For example, if a dog let's say any breed of dogs, okay, they would be closer to dog than cat. So how these meanings are represented in the vector space is how close they are in the vector space. So to find a word that is close to any of the words in the vector space, all you need to do is do a similarity search. Check which word vector representation is close by the word you're trying to find. And if you do that, you will be able to find the words that are nearby that is having the same meaning. Okay, I hope that makes sense. Okay, okay, okay. Coming here. Okay. So now what they are proposing is a method to do uh, and we demonstrate the word vector capture syntactic regularities by meaning of syntactic analogy questions and also be able to correctly answer what 40. Okay, cool, cool. Look at this. This is what I'm talking about. For example, if we denote the vector for word I as this is the vector for some word. Let's say the vector for the word dog. Okay, it will be a vector, it will be a long vector. Okay, a vector like this, a lot of floating points, numbers and all that. Okay, if this is a vector, if it were in 2D plane, it would just be two like this, right? And it will have one x coordinate, and this will have a one y coordinate, so it will be represented as a in the 2D plane. So if a word I has a okay vector representation xi and focus on the singular and plural relationship, we can observe that this relationship, it's merely equals to this relationship. What it really means is, now the relationship that is the plural or singular relationship between two legs. For example, the representation of apple and the representation of apples, they both will, if we do a subtraction between the distance between them, for example, in this case, in this scenario, the difference between any two, let's suppose this was apple and this was apples, and this was car and it was cars. So these distance will always be same because they are sharing a same relationship between each other. That is, are they plural or singular, whatever. You see, so we can define a lot of different tasks as such. That has been explained here. You can see good, better, rough, rougher. So the model is trained so that it can predict this word that's coming here: good, best, rough. I don't know what's rough's superlative degree, but you understand what it is. It is understanding the superlative degree, base and the superlative, base and the comparative. You can see the base and the superlative, base and the comparative, right? So that's what it means to be making this. Okay, coming there. So there are different relationship in itself. Singular, plural. This is the one we just saw. Okay, cool. Now the model has been trained to predict this dude, this guys here. Okay, and in the training process we are changing the vectors. That's, it's very important to understand what is being actually updated. We are actually updating the vectors of the words as such, and those vectors will be trained. That's the weights inside the vector will be trained as such. Okay, so coming up, this is the main idea behind the paper, the only idea that actually is in the paper. So coming into the related works, they have given a recurrent neural network model that could predict the, what do you say, the next word using these are the formulas. Okay, it's pretty simple if you know RNNs, that is recurrent neural network. I'll give a small recap of how RNN really looks like. Basically, it's deep neural network, but now what happens is every node or every neuron has a recurrent loop. That is, it will give in the input back to itself. So there is a recurrence, and also output will be given to the as it goes on in the any neural networks. Okay, that is RNN. So basically it has this timestamp. It's called timestamp. It can be as time if you're doing some time series analysis. Well, it can also be sequences of words. Any kind of sequence is denoted called as time in this frame of formulating any RNN models. Okay, so the time could be literally, it could be like, if we are putting in these words into the model. Okay, the word representation we study are learned by ear. So this could be the time 1, this could be the time 2, this could be the time 3, this could be the time. So basically, one by one we are giving it into the model, and it's learning and keeping a hidden state with itself, which will keep all this relationship together. Okay, so what I've done is I have made a small model which could do the same thing that's written over here. I urge you to read these this thing, the whole thing. So here is basically the structure, what is happening. This is the vector that we have, the current vector. Okay, and this is uh the weight matrix. The weight matrix, weight is something that we update, right? So this is the weight matrix that we have. This is the thing that will be updated as we learn over the time. And we are then, see, this is a bigger one, okay? We are downsampling it. The This thing is been downsampled to this size, and then there, these all these are actually, weight vectors. This one, and this one, all these are weight vectors. Okay. Okay, that makes sense, I hope. And these are the representation for the older words. For example, if this was the word distributed word representation, if I were at this point, all the information about this distributed and words will be here in this one, and I'm giving it back to itself. You see, it's a t, the s of t and t minus one. So there's a loop happening here itself. So I have the representation of all these words that are behind this particular word representation. So that could be a way of, making the model understand. So let's go to the code and see how this thing works. Okay. So this is the basically the code that we have. Okay. What we can try and do is predict. What I'm trying to do here is, these are the few training data. Let's literally just three, you know, three data that I have, and what I'm trying to do is help this model predict the next word if given context is this or any of the other context. So these are the training data that we have. The cat sat on, the cat is on, the mat is where the cat sits. So all this is in there, and now what I want the model to do is, the cat is sitting on. It's not explicitly anywhere written over here, right? But will the model be able to say the cat is sitting on mat? That should be the answer that the model gives. Okay. So now the training data is way too small, and it has been tweaked such that it gives a reasonable answer so that we can have a good understanding. It's kind of a dummy data in itself. So what gonna do is do we're gonna debug the whole thing. Okay. Debug. Let's debug this, and I hope I can zoom into it a bit more. Okay. Hmm. Okay, so I'm using PyTorch, by the way. If you have a little bit idea PyTorch, it's good. If not, it's okay. I mean, if you have idea about how TensorFlow works, that's also cool, because um, things work same. The RNN still is gonna work same no matter which framework you use. Okay. Okay, the class has been initialized. Now the vocabularies that we have, all the vocabularies that is in here has been assigned, has been already been uh, given to the given in the list of vocab. Okay, so the training data is also done. Everything seems good. Okay, just give me a sec. Okay, uh, sorry for that. Here, what we see is basically now we are creating the embedding. So all the PyTorch already have a module for creating embedding. So now the vocab size is 12, and the embedding, this is what we call hyperparameter, right? So now the vocab size, which is 12, this is the length of this whole thing. Okay, vocab size, we where do we initialize it? Okay. Okay. uh, okay, we are putting it right here, right? Vocab size is equals to length of the vocab. Dimensionality is 12 and hidden state is this. So basically these are the embeddings or the vector dimensions. So this is the number of elements in a vector for a word as such. Okay, then coming in, so it will create a 12 into 128 vector, which basically will be like a matrix with 12 rows and 128 columns, and each row is representing a vector for a word in the matrix. Okay, if that makes sense. Okay, here we go. We can see embedding is 12 into 128. Cool. RNN, you're now initializing the embedding. Length is given. The hidden dimensions are given. So it will also create a small one. Let's see what it created. RNN is basically this whole thing. Okay. Batch first is true. Batch first is basically if you want to do batch training and all. But what's the point? We just have like three of them. So it's all good. Uh, Output is basically the hidden state into the vocab. So it will be hidden. Hidden is 256 into 12. So output will basically be this big what do you say, big matrix of the whole thing, and we'll see how it works actually. Okay, that's better if I okay, if you want to see how this model looks like, model dot state dot state state, and here we go. Oh, damn. State dict this one. Okay, check all the weights inside it. You can check it out. Okay, so now it's gonna be a pretty big weight. Okay, so I won't be doing what I do should do that is I will show you one cool thing. Just check this out. Okay, these are the weights, the embedding weights that we have. Okay, we can see other weights as well. We can check out. I think this is the things that I already you know checked out before. Okay, just need to understand the embedding weights. Okay, now if you want to see the shape of this thing, you can check out the shape as well. See, these are the embeddings that we have, and if I put the shape, it is like 12 into 128. So think of this as like this. Okay, think of this as I can have this space. Tell you, okay, this looks like okay. Uh, this is a big matrix. Okay, this is a big matrix, and there are like 12 rows. Okay, whatever, 12 rows are there. So every row is representing one word. For example, in this situation, the cat sat on. Okay, the cat sat. So here it will be the. So bad. It's the. You know, first word, second word, third word, fourth word. The cat sat on, and these are just numbers. And how many numbers are there? 128 numbers. Okay. Now, while the training process is going on, I will update these guys, these numbers inside, which you can see here, right here. These are those numbers, There are 12 of these guys and 120 of these guys. Okay, so row and column. Now you will actually see these things being updated while it's been training, and I will show you how the updation will happen. Okay, so the model has been done. Okay, model has been created. We see the weight. There are other things also being updated. Okay, but we are not bothered with that. We want this one, so I'm just focusing on the embedding weights right now instead of that, because there are a lot of parameters inside it. If you want to check it out, I will show you. Like check this out. Embedding weights are there. Then the RNN hidden state ka weight hai, and there are like see, look at all these small things. HH, IH, LICC. So many of them are already inside it. You can check this out here as well. Embedding weights, this weight, that weight. So many. This is both the biases. Uh, okay. I hope that is making sense. I don't want to confuse you with all these jibber jabber. Okay, where is it? This is what we are interested in. Loss function is defined. Optimizers, using the optimizer, this one, and I haven't, you can put also a learning rate. Well, if I think it has a default learning rate, a special learning rate. I don't remember. Okay, you can check it out. What is the default learning rate for Adam? I think it has some. That's all good. Okay, we are doing it. We are in. Optimizer has been defined. Now this is where the training loop starts. And so epoch is one, basically zero, the first epoch that we are going in. Now see what is happening here. The input is the cat sat on. The target is supposed to be mat. Cool. That's cool. Going in. Encode input. We are now what's happening is check this out. Okay. Check this out. It's really important here. The input that we have, that is this dude, the cat sat on. Keep this in mind. We are taking the input, splitting it. This is a string. As soon as we split it, it will become a list with every. I will show you. That's so much better. I can just show the thing. What I can do is I can just go and like do this. Okay, something's wrong. Did I not do it properly? Okay, maybe something is. Okay, no worries. We can try it. You see the cat, this has been contributed to list. Now for word will have the first word will be the. Okay. Now we are going into the vocab. Vocab is where we will find the index of that word. So word was the index is basically zero. Okay, zero. The encoded input will be zero. Okay, as soon as I run this, it should give me zero. Okay, the first output, the word is the. Okay, now the first is zero. Then second word will be cat. That is C is one. So 0, 1, 2, 3. It should come as 0, 1, 2, 3 after the loop is done. 2, 3, and that's done. And it will give me a. Let's go inside and this is 0, 1, 2, 3. 0, 1, 2, 3. I hope you can see this. Okay. Same thing goes here. Now the target that we have is mat. We are checking the index of mat, which is 2, 3, 4. Right. The fourth is with mat. The 4. Okay. As you can see, the 4 is right here. Now optimizes it. What? Okay, if you are new to PyTorch, so how PyTorch works is it uses this thing called what do you say? Uh, Differentiable autograd. Sorry, autograd. It's called autograd. What it does is, as soon as you do a back propagation, okay, this function is called in. Okay, it will calculate the gradients for all the variables that we have. So every single one of these variables, will be calculated already. Okay, for every single variable, its gradient will be calculated. That is, its differentiation will be calculated with respect to the loss function. Okay, if you have an idea of how deep learning works, you must have got what I said right now, right? So in back propagation, what we do is basically take the uh, take the loss function and differentiate with respect to all the weights inside a matrix or whatever, and then for every single one of them we are trying to update every single output, right? That's how it happens. Okay. uh, but so what happens is if you go on doing it without making it zero, that is gradients keeps on accumulating. For example, the first propagation it did, it got some value for the gradient. Okay, and what if you didn't empty that gradient? If you didn't empty it, then it will keep on adding to the, if the first iteration the gradient was found for this element to was something, let's say something called as, it was 0.3, and the second time it was 0.1, so it will add into it and it will be 0.4. Okay, so it shouldn't be like that. Every time when it's trained, you need to find new gradients. So optimizes zero grad has been used for that very purpose. It's a very, very important thing in PyTorch. When you do training, you don't accumulate the gradients for every single weights. Okay, so as soon as I do this, it will empty out. Well, nothing is there right now because we haven't called in. So, but okay, you get my point. Okay, I can actually show you that model dot. I think it's called grad. If I go in and I say embedding, see if I go and see embedding. See what about this. Can I go like and say grad? Okay, that doesn't make sense. Just give me a sec. Okay, I should be able to see this. So what I can do is models dot embedding dot weights. Weights. Yeah, wait. This weight. Embedding dot weight. Okay, I got it. Now what we can do is see the grad. You can see the gradient inside it. No, there's nothing. It's literally nothing. You can see nothing here. So it's zero. Okay. Now check what's happening. Okay, hidden state is done. We are not using any hidden states. Okay, that's all cool. Initialize hidden state for I in encoder. Size encoder input is basically this dude. The size. So what I can do is I can just show you what's happening in here. It's 4, of course. Okay, it's a 2D array, so it's going to be 0, 1, 2, 3. Okay, 0, 1, 2, 3 will come in. I is 0 right now. I comes in, it puts 0. That is basically, let's see what we have here. The first tensor. Okay, what it does is it take one of them and put it into 2D array. So view is basically like reshape. View is basically like reshape in a numpy as such. Okay, model we put in the first dude, the first guy. We're gonna do more of that. Okay, it's going in. We are passing it to the embedding. The hidden layer is here done. So okay. Uh, Second one. Now we are passing in the other one. The third one. The fourth one. And here we go. So what did we get out of this? Now the output has these vectors. Let's see how the output looks like. Okay. You know what? I can just take it out, right? Take it all out, and that's done. Now check out the output. Output is this, which is, check out the size of the output. Output has a size of 12. Okay, so basically it's a 3D array of 12 of them, and 12 being the number of vocabularies, right? So we're gonna try. We're gonna do the softmax and all that. It happens behind it. Uh, Cool. So now the output is right here. We are gonna do this. So now what does the -1 do, right? It's actually pretty simple. You can check it out. What would the shape of this be? Okay. It just reduced one of the arrays. Like it was a 3D tensor, now it's a 2D tensor. That's what -1 does. Okay. The loss function is basically the output that you have and the output that you wanted. So we are trying to find the loss between these two. And the loss function that we have is cross entropy loss, right? Putting in all together, okay. Uh, let's see what happens. We are inside there, and as soon as we hit this, we will see a gradient. Now check it out, check it out, check it. The grad coming. You see, it was empty. Now we have a gradient. Okay, for the and the shape of this gradient is exactly the shape of the embedding that we have. That is 12 is 12 into 128. Now this optimized raw step is where the weights are being updated. Weights will be updated basically. We go check this out. Okay, these are the weights. Just remember this first one. Okay, 2055. Hmm? Hit the line. Uh, and then you go here and check it right now. So there is a change. Can you see the difference in both of them? Minus 0.1, minus some things have changed, right? You can see there's a slight change in all these numbers. This was of one epoch. Okay, this is just one epoch. We are gonna go 1,000 epoch, right? Do the same thing again. Does the same thing all over again. Okay, let's go till here. Debug it once more. Hmm. Well, I personally do not think there's a need for like a thousand epoch to train these three examples. But okay, uh, just for the sake of learning, we're gonna do it. Okay, gonna jump off over it, over this, done, done. This is also done, done, done. This is the first example, right? Doing the same thing over and over again. So now, check it out. What are the weights? What are the model weights? Model weights, grad, it is shown. The weights are these guys, and as soon as I hit this, weights will be changed to this. A little change 5.3 to 6.3. Okay, the first iteration. Next iteration, it will do the same thing. Now check out the other thing, which is the next example. That is 1 5. So in the next example, what do we have? We have the cat is on this example. Okay, it will go to the same process, update the. We will see how it's updating. Okay, and there we go, and that's done. One more time, three times, three examples. Okay, we are doing it like 1,000 times over the three examples, but that's all good. Now let's see what other weights do we have. There are significant change. We can see change, not too much. Okay, not needed. Okay, now let's see what do we have. We have the mat is where the cat. Third one is right in there. Let's see. Again, we are back to the one, right? Okay, so it's basically done. That's how the training works. Let's get to the point where we are done with the training. Okay. So now we are. This is going on like 1,000 epochs. Let's. Still training. We're not printing out anything, so we will just check out the loss and all there itself. Uh, okay. The training has been done. Let's see the loss we have. Loss is very small. As you can see, the gradient weights are being changed significantly for few of them, not so much for others. That's how it works. Okay, need to be significant. Okay, so they are being done. Now here what we are doing going to do is do the prediction. Okay, so basically take all of them, split them, and put it into a tensor. So it will have the tensor representation basically, like a tensor representation of all of them. One, four. Here we Okay, this one. You see, this is the representation that we have. 1, 5. Okay. Now we are gonna put this into the model, as you can see, one by one, you know, back into the model and see what it's gonna predict. Okay. Put it because already the weights have been updated, right? The embedding weights are being updated. We are putting back into this, and there we go. We got one. For the first word, that was and the cat is done. Ease is done. Sitting is done. On is done. I think I did a little too much. Predicted next word is mat. So we got the answer. The cat is sitting on mat. Okay, just so you know, I want to show you this part exactly what is happening here. Okay, just want to show you how things work, how softmax works. Maybe can show you a little bit like what probabilities are, how softmax works, and give you the answers right here in the code. Okay, okay, here we go. Okay, okay, it's gonna do the training and all that. Let's wait for a while. Um, So here what's happening is I'm going to show you what output looks like and then what this does and how we are taking out what argmax is. Argmax is basically telling you the position at which you are getting the highest number in the array, the list, whatever you want to call it. Uh, so now check out what output looks like. Output looks like this. There are this a there are 12 numbers. Okay, there are 12 numbers inside that. Now what I want to do is there are 12 numbers are the representation for 12 probabilities for the the vocabularies that we have. So now we have probabilities for all these ones like the, cat, sat, on, mat. So the one which has the most probability is the one we are trying to get out of this. So what we have gotten in more technical word is a probability distribution for this vocab. We got a probability distribution for this vocab. Okay, I hope that makes sense. If I do this, what we have is we basically got rid of all the other things, just the 12 numbers. And now check it out. What happens if I do this? If I do okay, I can do this. That is fourth one. Basically, it's telling me that oh my god, I can do instead of argmax, I can just do max. Okay, also be standing. Okay, so this one is the maximum one. That is this one. You see the fourth index. I hope that makes sense. The fourth index is highest 0, 1, 2, 3, 4. And argmax tell us which index has the highest one, as you can already see. Okay, then the item is basically to just get the number instead of this. I will just show you how the item works. So 4. So now all we got to do is go to the vocabulary, which is this long, all these vocabularies, and go to the fourth one, the index that is mat, and predict that one. This is the value is 4 here, right? 4 value, and go inside, and it's 4, cap 4, and there you go. There you got the answer. Okay, if you want to understand how softmax work, I have shown you a little something here. Okay, check this out. Okay, now what I have done is basically okay. If you want to see exactly how things are working inside of every single one, how the cross entropy is working, okay, It's illustrated here, right here. Okay, I'll try to explain it. So if you have an array, I told you there's a 12 numbers. These are the, let's say these are the numbers that we have. Here is different. Okay. If I have the 12 numbers, hmm, and what the formula of the softmax is basically e to the power x upon a summation of e to the power x. Well, summation of e to the power x is basically what it says is kind of a normalization of this this array. Normalization in the sense, if you add all these things up after doing a softmax, it will come to 1. It will be equal to 1. Okay. So always, if once the softmax is done or any kind of normalization is done, the this whole sample that we have, or the whole array that we have, if we add it all up, it will come as 1. And then coming out of it, we see this is the first one that we have, the numerator, that is e to the power x. The input that we have is put right inside, and I can show it right here, right? Okay, here we go. Okay, 12 numbers, all of them together. Here we go, and this is the numerator. This is the summation of the same thing that's happening here. And you see log. All you gotta do is, this is the formula for cross entropy, right? Cross entropy is basically just the negative of the log of the softmax of the target. It's pretty long, but you get my point, right? Now the target is basically the fourth one that we have here. Okay, target was the fourth one because in the actual training data set that we had here, right? The goal was to see the cat sat on the mat. The actual goal here was to find the cat is sitting on mat. The target was basically 4. You see, that is how you got this value. I hope that makes sense. Okay, if you want to see the loss, you can find out the loss as well. It's this. Um, okay. Apart from that, what I can show you is maybe change the value of this inside here. No, I cannot change anything. I have to, oh, what happened? Can't I copy? You get the idea, right? So this is how the softmax work. Okay. If there's anything else you want me to understand. Okay, so this is the RNN model and how we are able to predict the next word using the previous words. I hope that is sufficient for now. Coming back to our paper. Okay, coming back to our paper. So here the idea is of an offset. Offset being this. Offset is basically a distance between the two vectors. Okay, offset you can call it a distance between two vectors. It's how you will understand. Vector offset. Okay. Uh, okay. Vectors and methods. Okay, this formula is probably the most important formula out of all the other things in the paper. What it is essentially just dot product. If you know what dot product is, A dot B, right? A dot B is your dot product, and it's nothing really. A dot B, you can call it as uh, there's a way to call it like cos of A into B, magnitude of A and cos theta, or whatever the angle is between these two guys, and so that can work, or this can work. This is the same thing actually. It's also kind of a cross product between them. This is what we call as cosine similarity. So this is where the cosine thing comes in. Okay, what cosine does is, if you say cosine of 0 is 1. Cosine of 90 is 0. Okay, so if in a vector space, if we have this huge vector space, okay, this is the huge vector space as such. Okay, here we go. Now if there is few things that are like dog, dog, my god, I'm so bad at this. But you get my point. Okay, I'm just gonna draw this like this. Okay, there's few things that are similar to each other will be nearby. Okay, and few things that are away from each other, they will be a little farther away from that. Depends upon how dissimilar are they. Now if you really think about in the terms of cosine, uh if I take this dude and if I take this dude, the angle between them is theta, and cos of this small angle is higher. This angle, cos of this angle would be higher than if I take the same this vector and this vector. This is a bigger angle, right? Anyway, so this will be smaller because as you go like from 0 to 90, the value of cos of those vectors or those angles becomes smaller. Okay, and if you have something like something is here and something is here, they are in a 90-degree angle. Okay, they are basically zero. There are no relevance between both of them. It can also happen. Okay, that's what cosine similarity means. And vector offset was a method that was used to evaluate on these data sets actually. You can go check it out. Uh, so now RNN was used, the same thing was used, but now these are the hidden layers, how many hidden layers and how many, I think it was hidden layers or see it once. And there are a few parameters they have already stated that they have used in the paper. It's not rocket science. You read it once, you will be able to understand what is happening inside. Okay, total dimensionality. Okay, it's a vector dimensionality. If you saw right, the dimensionality was 80. This is and total dimensionality 1600. Okay, and this was their experimental, thing. So 80. So vector dimensionality is basically this one. What we have done, this embedding dimensionality 128. They have used way bigger dimensionality than we did uh, for 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 getting better accuracy. So as the dimensionality of the vectors becomes more, you can clearly see a raise in the, what do you say, uh, accuracy or the results. The Spearman, this is not used anymore to be frank. Uh, but yeah, but you can clearly see what's happening here. Okay, that's um, so on the biggest takeaway from this paper is that we are able to represent words in a vector space, in a continuous space. Okay, we are able to do that, not just uh, able to represent it but also able to understand the context that is happening behind it. Okay, so before that we had this n-gram models that I told you already, which was able to predict the next word given the previous words that we had, but it had no understanding of the context or anything. So this continuous space word representation was able to do something like kind of a relationship was established between two vectors, and this relationship can be mimicked for other relationships as well. So these are few of the takeaways from this paper. So that was it for the first paper. Next paper I have planned, that is distributed. Sorry, this is the paper actually. Distributed. Oh my god. Distributed representation of words and phrases and their compositionalities. So this is one of the groundbreaking papers in the NLP domain. As such, it was also given some prestigious award in some conference recently, like the biggest conference for all these research papers. So we're gonna do this. We're gonna code this as well. There is gonna be a really good code and I'm gonna explain this equations. What are these hierarchical softmax and negative sampling, how things work. Okay, subsampling we're gonna see by drawing. We will be plotting and stuff also. Okay, so this is a very interesting paper in itself. A little math heavy, but we'll try to make it as simpler as possible. Okay, then thank you for joining in, whoever were there. See you on the next stream, which will be on Saturday.